Hey, good morning. My name's Peter Felfer, and I'm going to show you how to use the XRNG editor, which is part of my openVA software package today. So in this video tutorial, the first 5 minutes, I'm just going to give you all the basics that you need to operate it, and it's going to be enough for you to make your XRNG files, and then I'll continue and give you some more basics and some more background. So just go into MATLAB. It's all written in MATLAB. Go into the XRNG editor Lite folder and type in XRNG editor. Next thing you'll get is a dialog to go to whatever .pos or .epos file you want to work on. I'm choosing this dataset that I've created with Betsy Clark from Santa Barbara. It's a superalloy, iron-based superalloy. And once you've clicked OK, it will create the master charge spectrum. Very simple, and there you can see the editor, and it defaults to horizontal zoom, so it just zoom into the section where the actual peaks are, and that's what we're going to work on. So the sections you have are ranging, peak identification, control for the secondary axis, save XRange in the end. Unfortunately, didn't have time to implement load XRange, so you can only create one and then save it. But since it goes pretty quickly, it's usually not that big an issue. And yeah, so that's what we're going to work with. So you've got the count per bin here, and you've got the master charge Daltons here. And here you've got the same master charge Daltons if you're going to go for anything in the secondary axis. So the way you go about doing this is first you let the XRNG editor know what sort of elements you've got in there. So it's iron, nickel, chromium, and we'll concentrate on the metal 2+ section. That's going to be enough for this tutorial. And then it can deal with complex ions. So you just tell it which elements form complex ions, which is hydrogen, carbon, nitrogen, oxygen. If you type in standard STD, 1 and 2 are the charge states to be considered, and 2 is the maximum hit multiplicity. That only applies if you've got an EPOS file. This is not an EPOS file, so it doesn't actually matter. And then you go suggest ions. Suggest ions means that you mark a peak and the program will actually suggest an ion for that peak. And then you go and pick one if there's multiple choices, which there usually are. And then it will mark that peak and calculate the height of the other peaks of that ion based on the height of that peak. And for that reason, you should always pick the highest peak because it's got the least background. Or you should always pick the peak with the least background if you've got overlapping peaks, of course. Sometimes that's not really working that well, especially if you've got elements with only one isotope. Anyway, let's just jump right into it. Go into the metal 2+ section. You can change the zoom options by right-clicking and go to vertical zoom or unconstrained zoom. Horizontal usually works pretty well, and shift zoom to zoom out, and then pan to pan, obviously. Then you click suggest ions. So the problem with MATLAB is it cannot switch from zooming or panning to hotkeys, which is a bit annoying. So for the first time, you always have to click with your mouse on suggest ions. Then you mark the peak here, and you'll get a dialog box which shows you which possible peaks are around and how far they're away from the suggested ion. So that's 0.13 Daltons. It means the charge spectrum is a little bit off, and the relative abundance of that ion. So iron 56, 98.8%, and it's very close, so it's probably that. And the other peaks fit as well, so which tells me that's probably the correct one. Then now you can actually use the hotkeys. So press P to mark that peak here, and iron 58, it's probably not that. So it's probably nickel 58. And if we're right, the other isotope, the other peaks, the peaks of the other isotopes should pop up properly. And they do, so that's all good. And that peak here is, I suppose, chromium, yeah, chromium 52, all good. Choose that, and we've got the chromium peaks. So once you've done that for all of your peaks, you can move over and do the ranging. Of course, you can do both things at the same time, but I tend to just do peak identification first and then do ranging. So you click Add Range. But since we're not zooming or panning at the moment, we can also press the hotkey R and then mark the range from here to here. So the height of the box doesn't actually have any influence, by the way. And we'll get that marked green. So it's marked this as the range for iron 56. And you can see that here it's all added and it already knows that it's an iron 56. Which is the multi-isotopes. That's actually pretty handy, especially if you've got super alloys, because there's usually a lot of peaks. So that'd be iron 57, nickel, and you get the idea. It goes fairly quickly. If you've got more than one, for example, here with the chromium and the iron, there's two things you can see. You can see, first of all, the overlap, of course, and that there's a green dot. So the green dot actually represents the sum peak. So you can check the height of some peaks as well. And the other thing you can see is that if you mark the range in here, it will pop up with a dialog, and a dialog will ask you what it is. This is actually mainly an iron 54 peak, so we'll just keep it default, click on to OK. If you have a peak where you don't actually know quite what it is, or you don't have an isotope, you don't have a peak identified, you can also go and manually type in what sort of iron it is. So just like here, if you type these things in, use the elemental symbols just with a space in between, and a multiplier. So, for example, Fe2O3, right? And then it will ask you to specify the isotopes, which of course in this case I'm not going to do because it's going to be five isotopes to specify. Okay, maybe I'll do so. And oxygen 16, oxygen 16, oxygen 16. And now I've got a iron 56, iron 56, oxygen 16, oxygen 16, oxygen 16, iron. Range. If you want to delete that range, just click on delete range, that area, and that's it. So once you're through with that, you just go save XRNG, test XRNG, save. Of course, there is already one, so we'll just go and replace that one, and that's it. You're actually good to go for your analysis. So that's the first 5 minutes, and now I'm going to show you some of the other things that's in there and some of the behavior for those that are interested in a little bit more in how it works. Well, first of all, what we have here is the secondary axis. So what you can do with the secondary axis, you can actually have a look at a deviation in mass to charge, which means it compares the position of the peak, of the closest peak next to an isotope peak to the location of the peak. So the deviation here is always positive and always around 0.12 Daltons, which means that our mass to charge calibration in this area is off by 0.12 Daltons. So the XRNG Editor Lite does not actually have the recalibration. The full version that I hopefully will be able to give out soon. You're just going to be able. You're just able to mark that and say correct, and it will actually correct the mass to charge spectrum, and also correct that in the .pos file which means that you can very easily do recalibrations. So if you mark that, it will actually calculate the average deviation. Then you can go deviation by counts, and this is to check whether isotope ratios are correct. And there are some considerable deviations here in some of the smaller peaks. It's mainly because there are overlaps, like the iron 57 peak, for example, has a good 20% overlap with the iron 56 peak. Because they're both iron, it doesn't actually matter all that much. Other peaks, it's sometimes a little bit more problematic. For example, here we've got a mixed peak. We've got an iron and chromium mixed peak that's about 10% overlapping. And average hit multiplicity obviously only works if you've got EPOS files. But anyway, so that's recalibrations that are available here. And then probably the most important thing is the behavior. This part here, which is the peak identification, because you're going to be using that quite a lot. And it's actually something that I personally consider very handy, because it doesn't just allow you to have a look where certain peaks should be, but also check the isotope ratios if, of course, your element has multiple isotopes, because a lot of elements unfortunately don't. A few important elements like manganese, gold, unfortunately don't. And so yeah, so when you type in for the peak identification, when you type in what's in there, just use the elemental symbols and spaces in between. That's all there is to it. If you have some misspelled ones in there, it will complain anyway. Then next thing is elements that form complex ions. These elements will actually be added to this list in terms of just the complex ions. So in other words, if I have carbon, nitrogen, oxygen, hydrogen here, and I've got hydrogen, iron, nickel, chromium here, what it will do is for hydrogen, because it's both here and here, it will search for hydrogen and hydrogen 2. For iron, it will search for iron hydride, iron carbide, iron nitrate, and iron oxide ions. And because carbon, nitrogen, oxygen are just in the complex formers, it will not search for carbon. It will just search for complexes that contain carbon. So if you think you've got carbon in there, like a carbon peak or carbon 2 peak maybe, you actually have to add it up here, right? Simple. Same obviously applies for everything down here. And it will search up to a complexity, should actually say complexity, not hit multiplicity, sorry about that. So it will search up to a complexity of 2, which means it searches, for example, for iron and iron carbide, but not for iron an iron with coming off with 2 carbons. So it doesn't do that. If you need to do that, which is especially the case for compound semiconductors, I've been doing some gallium arsenide recently. There, even if you measure it in voltage mode, you'll get arsenic 3s, arsenic 4s, a little bit of arsenic 4s. So you will need to crank that up to a higher complexity. So the reason why you wouldn't straight away crank it up is, first of all, every time you suggest an ion, it needs to build up the ion list, because it needs to check which ones you're using. So this will take longer. And the other reason for that also is that you will get a forest of peaks if you just hammer in too many elements, too many complex formulas, too many charge states, too many hit multiplicities. If you go overboard there, you'll just have peaks everywhere, and you're probably still going to be able to find what's relevant for you, but it's just going to slow down the process quite a lot. So just be very focused in what you're using here. And that's then, I think, for Light Editor, pretty much everything there is to explain, because I think add range, edit range, and delete range are pretty straightforward. If you have .epos files, you can actually define on where it's working on, so you can define the hit multiplicities you want to be working on. Especially, there's a paper by Lanciao where it's shown, for example, that in steels, carbon mainly comes off as multiple hits, as double hits. Then you can restrict your ranging to double hits, which can be very handy sometimes. All right, since we've saved everything already, we'll just go and open the .xrng file, open as text, just to show you what it looks like. Text file. Anyway, I'll close the XRNG editor. There we go. So that's just the .xrng file. It's a very simple XML file, so it starts with the tag for range file, version 0.1, ranges. It's got a master charge begin, master charge end, atomic number, isotope, volume, which we need for the reconstruction, so it calculates that. What charge state it is, so we can do charge state mapping, and of course isotope mapping. So charge state mapping if you want to know something about the evaporation physics, and isotope mapping obviously if you do. That was actually a much requested feature. It seems that a couple of people out there are doing experiments where they do isotopic diffusions and things like that. So the range file is pretty much down to here. So we haven't actually defined many ranges on here, just because it's a short tutorial. And then you have the identified ions, which is just the peaks that you saw, the red peaks. And you can go and have a look on how high the peaks were, where the peaks were, and what the isotopic combinations of the ions that you have defined now. This is, for example, it's very easy to see that that's an iron peak, so that's 2654 is iron 54, 2656 iron 56, and so on and so forth. So we didn't have any complex ions in here really. Then this list would of course be a little bit longer. And that's pretty much it. That's all that's in an XRNG file. For the analysis, really, because deconvolution is not really implemented yet, that's what this is actually targeted for. You will actually only need that, but we don't have to deal with that anyway. So that's it for the XRNG editor. I want to save that. Oh great, that's what happens if you update the MATLAB version. So anyway, that's it for